The disturbing part was not the signal strength. Some of these bursts carried more energy in milliseconds than the sun releases across entire days. That was measurable. Ordinary physics could survive that. What unsettled the room was the spacing. 3 billion years of travel time separated Earth from the source, yet the intervals kept returning narrow enough to recognize by eye. Small clusters, quiet gaps, familiar timing windows appearing again after months of silence. The graph stopped looking random before anyone in the room could explain what they were seeing. The replay had already started when another spike appeared beside it. Nobody in the control room reacted immediately because the first assumption was timing drift, a recording delay, some small failure inside the observatory pipeline. The screen stayed mostly black except for one thin vertical line cutting through the noise. Then it vanished again. Several seconds passed. Another burst arrived from the exact same region of space. FRB 1210-2, repeated from the same point again. That was not supposed to happen. Fast radio bursts were treated like cosmic accidents. A star collapses. Something explodes. Energy tears through space once, then vanishes permanently. Observatories recorded them, classified them, and moved on. But this one kept returning. At Arecibo Observatory in 2016, engineers replayed the signal while checking for instrument failure. During the replay, another live burst appeared beside the older one. Same coordinates, different arrival time. The third repetition changed the atmosphere in the room because the problem was no longer detection. The problem was persistence. The signal had traveled roughly 3 billion light-years before reaching Earth. Civilizations on Earth could rise and disappear during that transit time alone. And still it arrived in separated intervals sharp enough to recognize by eye. The screen would stay quiet for a while. Then, another narrow spike cut upward through the data. Not random enough to ignore anymore. Rows of burst timestamps began stacking until certain spacing patterns started reappearing across separate observation years. FRB 1210-2 kept returning inside narrow timing windows. Researchers pulled years of detections into the same graph. Most of the screen stayed empty. Small vertical marks appeared in uneven clusters, separated by long silence. The expectation was that larger datasets would dissolve the pattern into randomness. The opposite happened. Certain gaps kept compressing into familiar spacing groups. Short interval bursts appeared near other short interval bursts. Longer quiet periods returned in roughly similar positions. When technicians shifted two separated timelines over each other, several burst groups aligned almost perfectly. For a few seconds, the graph just stayed there on screen. No dramatic movement, no new signal, just repeated spacing that no longer looked comfortably accidental. The energy stopped being the part researchers argued about. The intervals did. At the Canadian Hydrogen Intensity Mapping Experiment, repeating burst catalogs kept adding new observations across multiple years. The structure survived longer than expected. Fresh detections strengthened the same interval families instead of disrupting them. A brief binary labeling overlay appeared during one comparison test. Not as a conclusion, just an attempt to compress the spacing into something measurable. The next burst sequence fit the same structure again. Conversation in the room became procedural again once the magnetar models appeared. FRB 1210-2 finally looked physically explainable. Simulations showed a dense neutron star rotating through violent magnetic instability. Plasma twisted around the surface. Radio pulses escaped through narrow regions as the star turned. On several displays, the timing overlays matched parts of the observed burst clusters closely enough that the room atmosphere changed almost immediately. People stopped staring at the signal like it was an intrusion and started treating it like physics again. In 2020, papers connecting magnetars to fast radio bursts made the explanation feel even stronger after a real magnetar inside our own galaxy produced FRB-like emissions. The mechanism no longer sounded hypothetical. A source smaller than a city could release impossible amounts of radio energy and repeat under the right magnetic conditions. The graph stayed orderly for a while. Researchers isolated plasma distortion models, rotational windows aligned with several known burst periods. The repeated timing no longer needed intention to explain it. Just magnetic stress, unstable surfaces, and enough energy trapped inside an extreme object. One late burst arrived outside the predicted activity window. Nobody reacted immediately because the simulation itself still looked stable on screen. The rotating model continued cycling normally, while the real signal drifted slightly away from alignment. Not completely wrong, just not completely solved either. The first disagreements appeared in the filtered reconstructions. FRB 1210-2 looked different every time humans refined the data. Side-by-side timing maps from different observatories began drifting away from each other. One reconstruction showed clean, clustered intervals. Another filtering method erased half of them completely. Bursts that looked structured under narrow bandwidth settings dissolved back into noise when processed differently. Then older archive detections were reprocessed again. At the Canadian Hydrogen Intensity Mapping Experiment and the 500-meter aperture spherical telescope, researchers compared timing behavior across years of observations. Some interval chains only appeared after deeper noise reduction. Other bursts, previously labeled interference, started fitting directly into the newer spacing models. One discarded marker was manually restored into the sequence during a review. The pattern changed shape immediately. For a moment, the screens remained frozen on two conflicting reconstructions of the same source. Neither one looked fully wrong. Neither one matched perfectly either. The signal kept inheriting structure from the way humans chose to observe it. The earlier confidence around the magnetar explanation still remained partly intact. Rotational activity could explain some timing behavior. Plasma distortion could explain irregularity. But the boundaries kept moving. A burst classified as random in one dataset became meaningful in another years later. The signal was not becoming clear with better observation. It was becoming more dependent on interpretation. Archived bursts continued replaying across the observatory systems long after the argument slowed down. FRB 1210-2 never stopped repeating. Rows of detections stretched across years of stored observations, while automated catalogs kept processing them as ordinary natural transients. New entries appeared. Classification tags followed automatically. The timing structures remained visible underneath the labels anyway. At the Canadian Hydrogen Intensity Mapping Experiment, thousands of fast radio bursts entered expanding catalogs over time. Only a small fraction received deep structural analysis. Most passed through filtering systems designed to identify categories quickly, not uncertainty slowly. One repeating burst appeared on the screen with the same interval family discovered years earlier. The software marked it natural before the comparison finished loading. Nobody in the room reacted strongly anymore. The discussion had shifted away from origin. The work now focused on classification consistency, signal confidence, bandwidth integrity. The burst replayed quietly behind the conversation. Some of these signals had already existed in archived data years before humans recognized they were repeating at all. The physics never fully broke. The energy remained measurable. The magnetar models remained partially functional. The timing structures stayed statistically arguable. What changed was smaller than that. Humans kept waiting for intelligence to appear in a form that looked unmistakably intentional. The signal stopped behaving like background noise first.